Uh, Very nice to be here. It's a pleasure to give a lecture at this school. I know you're already 3 days into it, so I'm going to sort of try to reinforce some of the things that you've been hearing about already in terms of finite volume methods, a very particular kind of method of many that you're studying in this next 2-week summer school. So I'm going to focus on these finite volume techniques for MHD, and with the wrinkle of how and what changes are necessary, or what issues do you have to think about in getting these methods to work effectively on GPUs, and more importantly, just sort of heterogeneous computing architectures in general. And I'll give a bit of an example of a code that's been implemented based on a code I think you've already heard about, Athena++. There's another version now, AthenaK, which is basically a rewrite of Athena++ to be able to enable it to work on GPUs. So it's a big topic, lots to cover, only an hour. It's hard to know what topics to focus on, what not to talk about. So I'm going to start with some really sort of review material, if you like, from the last couple of days, mostly about what data do you actually need to store on first if you're using a finite volume method, because that gets to exactly how you implement the code on a GPU. And exactly how parallelization works in most codes. Again, GPUs are essentially parallel architectures, and so you have to understand a little bit of parallelization. I'll say something about adaptive mesh refinement, which I understand you haven't heard a lot about. At least you haven't gone into a lot of the details. Again, please interrupt me with questions or tell me I'm going too slow or something. If you've already covered all this material, but I want to say something about adaptive mesh refinement, because again, that affects the way you implement the code, especially on GPUs. And then finally, halfway through, I'll finally get into an introduction about, what are GPUs, how do they compare to CPUs? Most importantly, how do you program GPUs? That's a very open question, a very fast evolving topic. So I'll give an example of one particular programming model that I've come to rely on called Cocos. And I'll give you some examples of how to implement things in Cocos. There are other programming models, and you'll hear more about that, I think, later this morning and this afternoon. But today I'll focus, and this morning I'll focus on this Cocos, and then I'll give a quick example of AthenaK. Okay, so let's start at the beginning with the equations, which by now you should be know and love. The equations of MHD, written in conservative form. These are resistive and viscous compressible MHD. So we have the usual continuity equation representing a conservation of mass, momentum equation, an energy equation, a total energy equation with all of the fluxes from viscous, Poynting, and Reynolds stresses there, an induction equation to evolve the magnetic field, and then some definitions of a total pressure, gas plus magnetic, a total energy, including magnetic, kinetic, and internal energy, and the viscous stress tensor. So basically, these four equations are the evolutionary equations. And the things you need to store are the density, 3 components of the momentum, and the total energy. Those are the fluid dynamical variables. So basically 5 3D quantities, if you like, if you're solving 3D problems. And then plus you need the magnetic field, 3 components of the magnetic field. Again, I think you heard about constrained transport and the ways of keeping div b equals 0. The magnetic field in constrained transport is centered on faces of the cells, and so it's stored a little bit differently. So you can split them into the hydro variables, sort of the 5 arrays you need here, and then the 3 magnetic fields you need here. Okay, so the equations themselves tell you what the conserved variables are that you need to store. In addition, it's very useful to have things like the pressure and the velocity around. So often you want to create arrays of those as well, so you can switch back and forth between them. So in fact, you probably store more than just the 5 plus 3 magnetic field components, 5 conserved plus 3 magnetic field. You probably also store 5 primitive variables as well, so you don't have to switch back and forth. So where do these things live on the mesh? So a finite volume method involves creating a spatial mesh, and then storing. Again, the most important aspect of finite volume methods is that you're not storing point-wise values of the dependent variables u. U is the vector of dependent variables. density, momentum, and total energy. You're not storing point-wise values of these quantities, but you're storing integrals over the cells. So integrals over some finite volume of that quantity. That's what you store at cell centers. So U is the evolved variables which are located at cell centers in a conceptual way in a finite volume method. Whereas the magnetic field in constrained transport is stored as the area averages of the magnetic field. Again, not point-wise values of the magnetic field at any particular location, but rather integrals over these areas of the cells stored at the faces. So in any finite volume method using constrained transport, you would have cell-centered quantities at the, plus these three components of the magnetic field, one at each face. So the basic quantities you need to store are these 5 components of the conserved variables plus these 3 magnetic field components at cell faces. And if you're doing 1D, 2D, 3D problems, the most efficient way to store that is just as a 1D, 2D, 3D contiguous array of data in memory. Of course, there's many ways you could structure the code. You could store the data, each cell, in a linked list if you liked. You could store them just as individual scalars in this linked list. But for performance, the best way is to store them, if you can, best way is to store them as 3D array. That way the data is all in contiguous in memory, and then memory access is much faster rather than having to go look up the pointers to each value. But there are different codes implement things in different ways. Athena stores these things as just contiguous 3D arrays. So that we'll keep that in mind as we think about how to put the data on GPUs and just on CPUs as well. There's another issue, boundary conditions. What are you talking about boundary conditions for? Well, in a finite volume method, you normally would set boundary conditions by setting so-called ghost cells or guard cells. You would set values in imaginary cells that extend beyond the mesh. So if the white area is the volume that you're integrating and these cells are the actual ones you're evolving, then there's these imaginary cells that lie beyond the computational domain where you set values to give you boundary conditions. So for example, if you have a reflecting boundary condition, you reflect the values in these 2 cells based on these 2 cells. And similarly, you can have inflow, outflow, periodic, whatever you like. And so you need an extra memory to store these ghost cells. And again, the most efficient way to store that is in the arrays themselves. So the arrays are not just dimensioned to be the size of the mesh that you're integrating. You have to add either 2 or 3 rows of extra cells at the beginning and ends of the arrays to store the ghost cells. Again, you don't have to do this way. You can make these separate arrays and store them somewhere else in memory. However, then accessing the difference formula which involves cells near the edges requires accessing those ghost cell arrays, and that makes the coding a little more complicated. So again, it's sort of most compact and efficient to store everything in one gigantic array, including these ghost cells. It does lead to an issue that you really don't want to have too small a mesh here, because otherwise the number of ghost cells begins to get larger than the number of cells you're actually updating. So here I've got like a 6x6 2D array, but there's more ghost cells than the actual independent variable you're raising. So 6x6 is too small. In fact, in practice, sort of 8 cubed is the smallest you ever really want to go in practice from experience. On a GPU, it's even bigger than that, 32 cubed to be the sort of smallest mesh block or mesh memory array that you'd want to use without the ghost cells beginning to add up too much, using too much of the memory. So the volume to area ratios of this design is a very important issue. Okay, parallelization. So modern HPC systems have a variety of ways of handling parallelization, including shared and distributed memory parallelization. We're going to get to shared memory parallelization a little bit later, because that's what GPUs are all about. But for distributed memory parallelization, that is parallelizing across nodes, across distinct processors that are independent from one another and connected on a network, then you want to use domain decomposition with message passing interface, MPI. Basically, the grid is divided into equally sized blocks, and each block is farmed off to a separate processor and updated. So for example, if I had this 2-dimensional mesh and I break it up into 5 by 4 blocks, 20 blocks in total, then this would run well on, say, at least 20 processors, or at least, this needs to be an integer or divisor of the number of processors you're doing so that the work is spread equally across all the processors. And then the Go cells are communicated between the processors using MPI. Now, I didn't talk about why these are different shadings in the Go cells, and now you can see why. And that's because if I imagine, say, this block 13, its ghost cells are an extra 2 range of cells around the edge of this block, but they overlap different blocks. They overlap the blocks on the neighboring faces, these 4, but also they overlap the corners, these 12 and 16 and so on. And so the shading is showing you from the different processors, you have to get the data. So to get the Go cells for this block 13, you have to communicate with all of your neighbors, your 8 nearest neighbors in 2D. That turns into 26 neighbors in 3D. So in 3D, then you would have to extend this mesh in the 3rd dimension, and now you have not only corners, but you have edges between the faces, faces, edges, and corners in 3 dimensions. Okay, so distributed memory parallelization is all about, in a finite volume method implemented in this approach, is all about just passing this ghost cell data from your neighboring processors and filling the Go cells. All you need to do to parallelize the code is basically to figure out all this ghost cell communication in 2D and 3D. Now in this plot, there's another diagram here, which is how to organize these blocks in memory, how to assign them an ID, how to keep a record of what they are. You could just have a Cartesian mesh of blocks and label the blocks according to X, Y, and Z axes on the mesh. And that works fine if you have a uniform grid, but as soon as you have a nested mesh, then the X, Y, and Z axes are no longer the same in the sense that there can be more blocks in X, Y, and Z at different locations. And so you need a different way to organize the data if you have AMR. And one very, very attractive way is to use so-called quad trees in 2 dimensions and oct trees in 3 dimensions. And so this diagram is showing you a quad tree that stores this data in 2 dimensions and enables you to assign neighbors very, very easily. And basically starts by a single node, which is the root. You divide that into 4. However, only these 2 nodes are going to have any data on them. These 2 are not needed. If I chosen an example in which the number of mesh blocks was a power of 2 in each direction, then the quad tree would have been full all the way through. But I specifically chose an example with a weird number of mesh blocks, 5 by 4, to show you how the mesh block tree is constructed in sort of more general case. In this case, the logical level 1 doesn't have data at every single node. Only 2 of the nodes require data because only those 2 nodes are going to have further leaves beneath them. So these 2 are then broken up again. This node corresponds to this block right here. It's completely filled, so these 4 blocks are needed, but this one only has these 2 blocks in it. So again, there's 2 nodes that are null. There's null pointers because you don't need them. And then finally, these red blocks are divided up into logical level 3 into each individual mesh block, and then those are assigned integer numbers. And again, not every single node is needed even at level 3, and so some of them are just null. So this is a convenient way to label all of the mesh blocks and order them in a list, and it has the great advantage of preserving locality. Your nearest neighbors are generally numbers very close to you when you're doing this so-called oct trees. It leads to the Z ordering automatically. And Z ordering is a way of rank ordering a set of numbers such that your neighbors are always nearby. And that's good because when you're doing communication on a network, you want to make sure that your neighbors are not way on the other side of the network many steps away. You want to have the smallest number of steps between you and your neighbors. And so Z ordering is a way to guarantee locality. So by adopting these oct trees, you have not only a very convenient way of organizing the data, but you also get locality, which helps performance on some machines. Great question.
Yeah, naive big picture question, but with the Go cells being sort of the mechanism that you're using to set your boundary conditions, would you not achieve the same thing by just controlling the outer edge of the active cell? Why put a whole another cell there and worry about its center instead of, for example, just controlling the flux on the outer edge?
You could impose the boundary condition through fluxes. You're right. You can impose boundary conditions on the fluxes. But for various reasons, it's generally more convenient to be able to set the boundary conditions using the actual cells themselves. And that's why we use ghost cells. But you could rewrite it in a way that you always have to set specific values of fluxes. That's right.
It's a case of convenience.
It's right. I mean, there are a few such codes where actually you can just set boundary conditions through fluxes. There's a specific example which escapes me right at the moment where using fluxes can be very inconvenient because you don't really know what the fluxes are supposed to be. Yep.
Yeah, I have a question. So
yep.
in the case of the logical levels, essentially are the subdivisions from each cell, right?
Say that again.
Essentially, I would like to understand how the logical levels are represented in the mesh.
So again, this is a data structure in Octree, which would just be represented by a class which representing a node in the tree, which has a pointer to all its 4 or 8 leaves. That pointer would then just point to instantations of that same class, which would then be the next level of that node. And you store things like the ID and your level in each of these class elements.
It's not related with the refinements, right?
It will be related to refinement in just a second, because the Octree is really needed for mesh refinement. If you're only doing uniform meshes, then you don't really need Octrees. You could just use these Cartesian grids or some other way. But as soon as you have AMR, then there's really you don't really have a choice except to have some kind of more advanced way of storing. Honestly, Octrees is such a common data structure in computer science, so I think there's even classes which implement this for you automatically. We rolled our own in Athena++ because we wanted the smallest Octrees possible.
Thanks so much.
Yep. Okay, so that in fact leads to AMR, which actually is a bunch of different algorithms. It's not just one way of doing it. There's many ways of doing it, and many codes do it different ways, and they're not the same. And the differences are really, really important. And the most important difference is just what the philosophy, how does the AMR work in practice? So if you have some region, this oval region, which you would like to resolve with a finer mesh, you can cover it in various ways. You can use so-called patch-based AMR, in which you lay down individual higher resolution blocks that cover this, this region of interest. And those blocks can be of arbitrary size and dimensions. You just choose whatever block most easily adapts or fits the structure you're trying to cover. And so the mesh blocks are all different. The patches are all different. And they overlap the fine patches below because they're of different sizes, and you can't predict. You'd have these weird shaped boundaries inside your mesh. You store all the levels at once, and you just interpolate back and forth between the fine and the coarse levels as needed to cover this patch. And it has a great advantage of being the most efficient in terms of number of cells in covering, or almost the most efficient. It is the second most efficient. Or you could use the so-called block-based AMR, where the background computational domain is broken up in individual blocks, kind of like this domain decomposition, in this case into a 3x3 mesh of blocks. And then you're only allowed to refine a given block. And so this 3x3 block would need to refine these 5 blocks, and then these 4 could be further refined, and so on and so forth. As you can see in this example, it leads to a much larger volume being covered with finer cells. So there's many, many more cells that you generate in this process. But because everything is so regular and all the mesh blocks are identical, it works extremely well in modern HPC systems, especially parallel systems, because it's very easy to program and load balance. And so in fact, this approach on large computers is generally more efficient than this, even though it requires more work. Flops are free, and so this thing actually runs faster than something which has less actual work, but can't be implemented as efficiently. And finally, you can have a cell-based AMR, where then each individual grid cell can be refined. Now, that wouldn't work in the data structures I've already shown you already, where we already have blocks and three-dimensional arrays. But if you stored your data in a way as individual cells, then you can do whatever you want with each individual cell, and you can break them up into more cells. So this is another way of doing it. This is the most efficient way because it uses the fewest number of cells. But again, there's an efficiency issue because accessing the data, since they're not in contiguous 3D arrays, is a bit slower. And so on exascale machines, this block-based AMR is emerging to be sort of the most attractive way of doing it in terms of getting the highest performance. And again, I've tried to list a few codes. There's many, many more that adopt AMR, but I think it's fair to say that these codes all are good examples of each individual kind. Some called Amrex, Chombo, and the Pluto code, which based on Chombo uses this patch-based. Athena++ use this patch-based Flash, and the new version of Enzo is switched to this block-based. And then Ramses is a very well-known code, and you should have heard lots about it on Monday, I think, which uses the cell-by-cell refinement. Okay, so obviously the way you implement these different forms of AMR is going to be completely different. So the very first thing you have to understand about AMR is what kind of AMR are you using, and which one. There's actually no really good, thorough study of which one is the best. There is no best. It depends on your application, and so sort of just be aware of how each one works. And so just to go back to these quad trees and oct trees, this is where AMRs really shines. So I go back to this, or where this oct tree really shines. If I go back to this example of a 5x4 mesh block, and then I imagine there's one little region where I want to refine it through 2 more levels, then if you have an oct tree, it's very simple to do that. You just insert new nodes. Whatever node you're going to refine just becomes another node of another level in the tree. And if you want to further refine that node, you insert another node again. And then you just automatically number the blocks again. And you automatically get Z ordering even on the AMR mesh. And again, this is why if you just had a Cartesian grid, it's impossible to label these mesh blocks in a Cartesian grid in any sort of sensible fashion. And so that's why these Cartesian orderings doesn't really work. You got to find some other way to storing the data. And these oct trees are really a nice way to do it. Very simple once you get used to working with it. Okay, so that's the real reason for using it. Okay, the last couple of things about AMR is criteria. Basically, you can use whatever whatever aspect of the solution or problem you're studying that's important to you. You can use that as a refinement criteria. How do you decide which blocks to refine and which ones you don't refine? That's completely up to the user. You can use thresholds on the conserved or primitives, densities above some value, densities below some value, then refine. You can use gradients. If the gradient of the density is above some value, if there's a shock front there, or the gradient of the pressure is above some value, or any function you like, you can just make it, do whatever you like. It's completely free. There are, those are the most common functions to use, namely thresholds and the density or gradients, but there's obviously complete freedom what you do. And of course, the skeleton in this closet is that, in fact, the solution will change depending on what criteria you choose. If you run exactly the same problem with one AMR criterion, and then you run it again with a different one, the mesh blocks are going to refine differently, and that's going to affect the solution because you're going to have more resolution in some places than others in a different way, and that's ultimately going to affect the solution. The question is whether or not the results are affected, because there's a difference between the solution and the results. By solution, I mean the individual point values in every grid cell. By results, I mean what it is you're trying to measure, how much mixing, what's the mass flux, what's the momentum flux and the turbulence. If those things change when you use different AMR criteria, then you're in big trouble because you don't have a converged solution and it depends on what you chose or not in some arbitrary quantity. And that's a big problem. So you want to make sure that at least the results, the things you're measuring from your simulation, the things you're trying to learn from your simulation, those are robust against the refinement criterion. And no matter what criterion you chose, you would have gotten the same result. Honestly, that's a black art. And not everybody does that. They'll show you a wonderful calculation, but there was only one calculation with one refinement criterion, and they never changed it. And you don't know. So you should always, in your own work, be skeptical and keep trying different things to see exactly what's going on. Okay, some more things about AMR, and then I think I'm pretty much done on AMR, which is a couple more things. Prolongation and restriction. When you create a refined region, you have to interpolate the variables to the finer mesh, and that's called prolongation. And how you do that in a finite volume method is you generally adopt the same monotonic interpolation methods that I think you heard about on Monday and Tuesday. For example, piecewise linear or piecewise parabolic or Weno or Weno-Z, whatever, or MP5, whatever reconstruction algorithm that you like, and you're already using on the spatial mesh, you can use that for the monotonic interpolation needed to do the prolongation step. And notice I've shown you one cell into 4, but to do this interpolation, you're going to need the neighboring cells to create the slopes you need to calculate the gradients. In fact, it's sort of worse because I was going to use the board, but maybe I can just show it with my fingers. The cell center here is located there, and the cell centers for these cells are not at the same Y location as the cell center of your original mesh. So to get these cell centers, you automatically have to do a multidimensional interpolation. You need to interpolate, a quarter of a grid cell away from the cell center left and right, and a quarter of a grid cell up and down, if you like, in 2D, and in 3D you need another one. So it's automatically a 3-dimensional interpolation that you need to do this prolongation step. And therefore, when you're near boundaries, you're going to need ghost cells to be properly loaded to be able to do all this interpolation in multi-dimensions. You need to cross derivatives to do this properly. So you got to make sure that the entire, ghost cells, including the corners, are properly loaded before you can do this prolongation step. And that's what can make the prolongation intimately related to how you do the ghost cell communication. And most bugs you get in AMR come from not having properly loaded ghost cells before you do this prolongation, in my experience, at least in Athena, that's true. When you destroy a finite region, then you need to average through actually this says interpolated. The variables must be restricted to the coarser mesh. They must be averaged to coarser mesh. There's a typo there, and that's called restriction. Now, because of the conservation laws, that's easy because I just need to take the total amount of mass by these 4 cells divided by the volume of the new cell, and that's the new volume average density that I'm going to store in the cell center. Similarly for the momentum and energy, and so conservative averaging makes this step local. I don't need any ghost cells, and it's it's sort of easy to do it this way. However, once again, there's skeletons in the closet here. You're going to destroy kinetic energy when you do this, because you can have 4 velocities in these cells, which when averaged together gives you, say, 0 velocity in this new cell. If you had, say, a vortex in here or something like that. And so the kinetic energy that was in these cells is going to disappear. But this is a conservative scheme, so total energy must be conserved. So that means the total internal energy of this cell must be higher, so that the sum of internal plus kinetic energy in this cell is the same as the integral of the 4 there. So that means the temperature and pressure in this cell can be different than the average of the pressure in these 4 cells here. That's unavoidable consequence of conservative averaging, and can be a real problem if you're doing radiative transfer and you have opacities that depend on temperature, and then it's going to be different on the coarse versus fine mesh. What are you going to do? You sometimes have to interpolate derived variables or prolongate or restrict at least you have to be aware of this issue and think about what you're doing, because sometimes it can make a difference. Okay. So you also need this when you're loading Go cells. It's not just when you're creating and destroying meshes, but when you have a fine and coarse boundary, two mesh blocks at two different resolutions, then the Go cells of one mesh block coming from the neighbor will either have to be prolongated or restricted, depending on whether the neighbor is coarser or finer. And so you have to do all this prolongation and restriction in the boundary communication step as well. And again, that makes you have to have all those Go cells loaded properly. In fact, with AMR, at least the block-based AMR, the good thing is that all of the AMR is built into the boundary conditions. That's the only place where AMR ever enters, is where you're doing fine coarse boundaries. So in their code, all of the AMR machinery is confined to a very specific piece of the code, which is the boundary communication part. The bad thing is the AMR is all in the boundary communication, and it makes it a horrible mess. Because, for example, let's take an example where you have two mesh blocks at coarse levels next to these four mesh blocks at finer levels. Let's take mesh block A and think about how it communicates to mesh block B. Well, mesh block A is going to have to communicate these three cells into the so-called coarse buffer of mesh block B, these are at the same level. And then these three, moreover, you're going to need these extra three cells here. You're going to need these two triangle cells here, because ultimately you're going to have to prolongate these three cells into these blocks here, which are the actual Go cells at the fine resolution of mesh block B. And so you got to do this accounting where you make sure that you're loading all of the boundary buffers, including the neighboring at the coarse level, before you can do the prolongation properly. Similarly, if you're looking at mesh block D here, which overlaps in this corner, you got to make sure you're communicating these corner ones properly. This is one example, and in 3D, there's many sort of special cases you have to take care of in your communication. Make sure that everything's loaded properly, and that gets to be, you have to be very careful in implementing all this. Yes.
Is there a limit of the refinement level between adjacent blocks?
Yes, good point. And I failed to say this, but in almost every code I'm aware of, there's a limit of a factor of 2 between the mesh block boundaries. And that's mostly because much more than that, and then your solution is completely dominated by the interpolation errors you need to prolongate and restrict. In other words, your prolongation and restriction operations are only good to, say, second order. And there's no point in resolving a large, or trying to prolongate a very large factor in spatial scales through some low order interpolation scheme. So you really never want to have a difference in refinement levels by more than a factor of 2 between levels. Yes. Yep.
How do you determine what level of refinement is necessary for a region of interest?
Another excellent question. I mean,
to complement, because when you have a simulation, maybe you start to increase the resolution to say, okay, after that resolution, maybe you obtain the same results.
Right.
And what kind of test what can do?
Yeah, I mean, I go back to this slide here. It's the same point I was saying here. I mean, forget about AMR. Just use a uniform mesh. How do I know my resolution was good enough that I have the right answer to whatever thing I just computed? I mean, this is the whole issue of convergence testing. The only way you know is to make sure that if you run a higher resolution simulation, the results, not the solution, because the solution will change. At higher resolution, you're effectively running a higher Reynolds number flow, and that's going to have a different solution. But the results that you're measuring better not change. Of course, sometimes you can't afford to do a higher resolution simulation. So you should at least do a half resolution simulation. You can afford to do that. Whatever the highest resolution simulation you run one at half that resolution. And if those two are different, then you have to be worried, because you're not quite sure that if you went one more step, maybe that would be. So if you're doing that already, there's no difference with AMR. Basically, how many levels do you need? That's a very solution dependent thing. You have to try increasing the number of levels you're using and see whether or not the solution changed. And it sort of goes hand in hand with the refinement criterion, because the number of levels you use and the refinement criterion can be sort of degenerate. You know, changing one might change the other. And so it's something that there's no mathematical proof you can use for a given problem what you need. You just have to experiment and know your physics problem and know what you're trying to measure and know what it depends on and make sure you're using that. Not the best answer, but that's the way it is. Yes.
Could you elaborate on this communication between mesh blocks? When you use an implicit algorithm, every block is dependent. Do they wait for each other?
So in the techniques I'm describing here, these are all explicit finite volume time integration methods. So everything is done explicitly, and every time step of the method, in fact, every sub-step, if you're doing an RK2, RK3, RK4 time integrator, having 2, 3, 4 steps, then each one of those steps, you have to communicate your boundary conditions to make sure that the sub-steps have boundary values which are in sync. And so then all this boundary communication is happening at every sub-stage of your time integrator, whether it be RK4, whatever it is. You're right that implicit methods are completely different. They become essentially elliptic problems. You have to solve the entire mesh implicitly at once. That's a whole nother lecture, a whole different approach. These are all explicit time integration methods. Yep.
With the prolongation restriction, are you able to track, say, I mean, if you're running a simulation, you have time steps, are you able to track, I guess, those cells through those times, or are they reorganized in the block tree?
In AthenaK, at least, or in Athena++, they are destroyed and they're lost in their gain. If you create a new mesh block, then you just gain a whole new block of cells that didn't exist before. As if you then destroy them, if you de-refine, then that data is not stored. You throw that data away, it's gone. You conservatively average it to the coarser grid. That's the only way it lives on. The rest of the data is gone.
It's hard to see that happening besides through AES.
Right. I mean, of course, there's counters that are measuring how long it's been since things were refined, and how many cells have been refined and how many mesh blocks. So there are diagnostic things that we keep track of just to monitor performance in terms of the actual solution. For example, another detail is you don't want to refine and de-refine every time step, because you can get into this pathological situations where one time step it refines, creates a whole new mesh block, checks refinement criteria and says, oh, I don't need to refine, I'll de-refine. De-refines everything, you're back again, does one time step, it refines, it just goes back and forth. If you're right at the boundary of your refinement criterion and you got floating point numbers, just the round off area or truncation area can make you go back and forth on the criterion. So you always want to refine and then leave it alone for 5 time steps or some number of time steps, and then check whether you should de-refine to make sure that the solution settles down to its new resolution and move forward. So you do things like that to make things move along more smoothly. Another aspect of AMR is flux corrections. There's a question about boundary conditions and fluxes. So this is where the boundary conditions are really important, and namely, boundary conditions and fluxes are really important. Namely, when you have a boundary between a coarse mesh and a fine mesh, and if you're using the ghost cells to calculate the fluxes for these things all independently, so you're going to calculate the blue fluxes on the coarse mesh using its ghost cells, and then you're going to calculate the red fluxes on the fine meshes, and there's 4 of them here. Those are going to be calculated using the ghost cells and those blocks all independently. There's no reason why the sum of these 4 red fluxes equals that blue flux, but that's a disaster if they don't, because then you're not enforcing conservation. You could be removing more mass from this cell than is entering those 4 cells, and therefore you're creating or destroying mass in the calculation. And so you have to make sure that you sync these fluxes. You always assume that the fine fluxes are more accurate. So you would average together these 4 red ones and replace this blue one with the fine mesh fluxes. So at the boundaries between fine and coarse meshes, that's the one location where you do enforce the boundary conditions via the fluxes and by your neighbors. And that's crucial to make sure you have conservation, prevent spurious reflections at fine coarse boundaries. Yet another communication step required in AMR, because generally these blocks are on different processors and you got to move the fluxes back and forth. And then the final bugaboo with AMR and parallelism is, and I haven't got the GPUs out, I better pick it up, is load balancing. And this is probably the most complicated thing about AMR and parallel machines, is that you want to make sure that every processor has the same amount of work to do. That's called load balancing. It's easy if you have a uniform mesh, because you can just choose how many mesh blocks you have to fit the number of processors you're going to run it on. But with AMR, the number of blocks keeps changing. You have no control of that. It's going to create and destroy new mesh blocks. And what's even worse is that with Z ordering, the mesh blocks have to be stored in a particular order. And if you create a whole bunch of new mesh blocks, that can affect the ordering and all the other ranks. And I'm supposed to give you an example, and this is where I will use the board. You know, suppose I just had a simple example of, say, a calculation on 4 processors. This little line here is supposed to represent a list of mesh blocks. 16 mesh blocks on 4 processors, 4 on the first one, 4 on the next, and so on. Perfect load balancing. This is going to run great. And then at some point I decide, or the algorithm decides, it wants to insert some extra mesh blocks. It's going to refine this. So maybe it's going to create 4 more mesh blocks and insert them in there in this Z ordering list. Suddenly this processor has 7, because you destroy that one and replace it with 4. That's very badly load balanced. So you're going to have to reshuffle the mesh blocks. But I can't just take these mesh blocks and put one there, one there, one there, one there, because then I've destroyed the Z ordering. Because this mesh block is, you know, if it's stored way over there, its neighbors are over here. And so what I have to do is actually move that mesh block over there to make room. And then I got to move 2 mesh blocks over there. And then I got to take that one and shuffle it over there. And so with Z ordering, you know, inserting mesh blocks in one rank can make communication happen on all the ranks everywhere, because suddenly they all have to shuffle over one step to make room to insert or destroy mesh blocks in their team. Now, fortunately, the communication step that this requires is actually fairly efficient, can be hidden behind other things. So in reality, it doesn't cost, but it does cost, but it's not like a showstopper. It's definitely an issue. And you got to measure it and be worried about it, but it's not a showstopper. Yes.
Okay, because why necessarily is having uneven distribution bad?
Well, assumingly each node in the machine has got the same performance. And so if this one's updating 4 mesh blocks, but this one's updating 7, this one's going to take a lot longer to finish. And that means that all the other processes are going to be waiting 3/7 of the time, while this thing is busy all the time. And that's bad, right? You want all the mesh block, all the processors to have roughly the equal amount of work. So they're all going to get to the communication step at roughly the same time and do all their communication together when needed. That no one's waiting for some one poor processor that's doing a whole bunch of work, much more than all the other ones. Okay? I can't resist with one more thing about AMR. Should we expect everything to be the same with AMR versus the uniform mesh? This is an example that Chris White found in doing testing of Athena++. This is a relativistic Kelvin-Helmholtz test problem. There was initially a shear layer, and this was KH unstable, and it rolled up into these complicated structures. And if you zoom in to one little patch of it, you can see all this fine structure, which is captured beautifully with AMR. When you use AMR to resolve this interface, you find much more small scale structure. This is plotting the density in this case and the ratio of the parallel to perpendicular magnetic field. It's a magnetized cage test. You can ask, well, is this converged? Is this the same? Well, so Chris then tried running the same calculation at the highest resolution in this AMR calculation just to see what it looked like. And it looked like that. Totally different. It turns out that this KH surface is only unstable to this one large scale mode. And all this substructure are all secondary instabilities that are induced by perturbations from the AMR mesh. It's not wrong per se, in the sense that this interface is unstable to secondary instabilities, but on a uniform mesh, there are no perturbations. There was only the initial sine wave perturbation, which gave you one roll up, and nothing else was, excited, and so there were no more other instabilities. But with an AMR mesh, you have all these fine coarse boundaries, you have prolongation interpolation, you have round off error inevitably, and the round off error is not uniform everywhere, and so that's a perturbation. And so you seeded a physical instability, but the seeds of that instability were all numerical. And so in reality, in nature, nothing is ever going to be absolutely perfectly smooth. There's always going to be noise everywhere. In reality, this is probably more realistic. If there's a secondary instability, it's probably going to go unstable. But you just have to be, it's just another interesting warning. The solution could look completely different with AMR versus uniform mesh for reasons that you can understand, and you have to decide whether those reasons are important or not. And again, it's just a warning to you. Sorry, 45 minutes in it, and I finally get to CPUs and GPUs. Okay, that's good. There's been some good questions. CPUs and GPUs. Okay, so what are we talking about? A modern CPU, let's try to talk about doing all this now on GPUs. You probably already know about doing this on CPUs, and in that case, you're thinking about something like Intel Alder Lake. It's a current generation of Intel CPUs, costs about $500 at Best Buy, gives you about a teraflops, double precision, has 16 cores, typically. Modern GPU would be an NVIDIA A100, for example, although there's newer ones now, but A100 is sort of workhorse. 10 teraflops, peak double precision, 80 gigabytes, cost $15,000 to $20,000. So, there's a lot of hype about GPUs and what they can do. And a lot of this is incredibly unfair, in my opinion. When you say, oh, my code runs 100 times faster on a GPU. Well, first of all, usually what they're doing is comparing the entire GPU to one core, which is crazy. There's 16 cores. So you want to use all the cores in the CPU at least, right? That'll give you 10 times more performance typically on the CPU. So a 10-to-1 performance ratio is pretty good. 10 times faster than an entire CPU is and that's exactly what you should get. That's the ratio of peak performance. But then look at the price difference. This thing is 30 times more expensive. It's a supercomputer. Of course, you should be getting 10 times more performance. It's a supercomputer. It's a $20,000 supercomputer compared to a $500 chip. I mean, it's just not it's not an apples to apples comparison. In fact, GPUs are not very cost effective. They are much more expensive per flop than a modern CPU. So why is everybody using GPUs? It's because they're so power efficient. And the limiting factor in building a computer today is not money. It's not the DOE doesn't have enough money to build computers. It's that to get enough electricity into a building to build a supercomputer, that's the limiting constraint. And so since GPUs give you more flops per watt, they're more efficient in terms of power usage than CPUs. That's why all the biggest computers nowadays are using GPUs. It's not because they're more cost effective. Yes, they're faster, but of course they're faster. They're way, way more expensive. They're much, much more complicated things. Should we use GPUs? Of course we should, because there's so many amazing machines right now that are using GPUs. But there's a problem. These are heterogeneous machines now, heterogeneous architectures. They have much more complicated architectures. They have multiple memory spaces, RAM, GPU scratch memory. They have different execution spaces. You can run on the host, you can run on the GPU. Sort of schematically, a normal machine would just be this CPU plus some main memory. That's your laptop, basically. Nowadays, you got a CPU plus main memory, plus maybe one or more GPUs attached to main memory. Sometimes you have FPGAs. I won't say anything about those, but in principle, you suddenly have to worry about data being in not only the RAM of the nodes, but also the RAM of the GPU, which is distinct, and you have to keep in sync. And it's up to you. And You can't, where are you going to execute the work? I mean, you can't operate on the CPU on stuff that's on the GPU. If the data is here, you can't do calculations on it here. So you have to worry about this new degrees of freedom you suddenly have on the GPU. So programming is much more complicated. You as a programmer have to control where you're going to put your data and who's going to do what the host's going to do and what the GPU is going to do. And you got to, manage shared memory parallelization within this node, and you also have to manage the distributed memory parallelization across all the nodes that make up this entire machine. And because of that, because most codes you're dealing with right now that were written for CPUs don't have these degrees of freedom built in. They don't have the concept of multiple execution spaces and multiple memory spaces built into the code. Generally, it can be quite difficult to port an existing code to GPU. It's probably better just to start from scratch and design your code from the get-go with these concepts in mind. And why should you do that? It's because it's just an amazing time in computational science right now, because exascale has finally arrived. We now have these machines in the US and in Europe as well that are absolutely amazing in their performance. We have machines like Frontier, 38,000 AMD GPUs, 1.5 exaflops of total performance. Aurora, which is coming online mid next year, 55,000 Intel PVC GPUs is going to have 2 exaflops of performance. These machines are 100 times faster than existing machines typically. And the amount of time that's being made available for open science on these machines is outstanding. Billions of core hours of time are being allocated for open science projects. And so there's an enormous amount of available computational time. However, you have to be able to run on these machines. And so if you're interested in running on the largest scales, then you have to adopt to that, because that's what the vendors provide. That's what they don't give you CPU machines at the scale, they give you GPU accelerated machines. You don't have to use these machines if you don't want to. You can run on CPU clusters and you still do lots of science. But if you want to run on these machines, then you have to be thinking about GPUs. Now, the problem with these machines is that they all require a different programming model. This is the other dirty secret of GPUs. You can't just use C++. C++ won't run on an NVIDIA GPU. You have to use their programming model called CUDA. But CUDA doesn't run on the AMD GPUs. They're a different vendor. Why would they support NVIDIA's program? They have their own, of course. They have something called HIP, which they invented. And similarly, Intel is not going to support CUDA. They support something called SYCL. And so even if you write a GPU code and say, oh, this is great, suddenly you're stuck. If you wrote it in CUDA, you can't run on Frontier or Aurora because those are different GPUs. And so you need a programming model that can run on anything. And that's where this Cocos comes into play. It's an open source code project out of the DOE at Sandia National Lab. It's basically just C++, C++ templates and abstractions for data containers and parallel execution strategies. You basically just clone the entire Cocos library as a submodule of your Git repo. So that you just have this raw C++ code. You have to adopt the C++ 17 standard, but that's all you need. And then you just build Cocos along with your application code using CMake typically. And when you build it, it automatically turns it into CUDA, OpenMP, SYCL, whatever it is. Basically, Cocos implements all these backends that automatically is like a translator. It turns the C++ templates into CUDA, which then gets compiled by the NVIDIA compiler as if you'd written your code in CUDA. Or if you instead during the build said, make it for an AMD GPU, it would have turned it into HIP. And then the AMD compiler will just say, oh, look, you wrote your code in HIP, great, I'll compile that happily. So it takes all of the work and concern out of your hands, and it's all built into the back ends on the Cocos, and it results in so-called performance portability. Finally, you can write a code that will run on your laptop if you want using C++, or it will run on the world's biggest exascale machines in whatever architecture they have, as long as Cocos supports it. It'll run on your iPhone because they support the ARM processors that Apple uses on your iPhone. So you can run it on virtually anything, anywhere, as long as Cocos supports it. And since there's such a huge team working on this. I think it's going to be around for a while, and they support pretty much everything. So I got 5 minutes left. What should I do? Should I continue going into some of the details or skip some details?
You can take another 5 minutes.
Take an extra 5?
Yeah.
Is this okay? So I'm going to destroying your coffee. I'm sorry about that. So there's a few, giving you a full tutorial on Cocos and exactly how to program is probably not the right thing to do here. But there's a few concepts that are worth knowing about and how things are different in Cocos versus C++. And the first thing that's different is the data structures. The most important thing to know about is something called a Cocos view. They've implemented a C++ class that implements basically 60, 1D to 60 arrays. C++ and C has always been a shortcoming. They don't have a native array class. Well, this implements a native array class for you, if you like, which handles allocation and deallocation and reference counting for you all automatically. It optimates memory layout, including padding. It does all the memory space attributes for you. And you can tell Cocos whether you want these arrays to live on the GPU or whether to live on the host when you construct them. So for example, some examples, here's an example of a my array, which is being constructed. The angle brackets are the arguments to the Cocos view constructor. It's a double. It's going to have 3 dimensions determined at runtime. That's what those 3 stars are. It's going to be layout right, meaning the right index is going to be indexed fastest. You could say layout left, and so it'd be like Fortran-like. The left index is fastest. And it's going to live in the default execution space memories, which if you said the default execution space is going to be a GPU, it would live in the GPU. If you told it to be a host, it would be the host. And so this looks ugly. You can wrap it all in your own classes, and that's what we do in AthenaK. We define something called a device array, 1D. And so you just need to define a variable type device array, and then it will automatically be created on the device as a 1D array with all the attributes that we have preset in AthenaK. And so by using simple wrapper classes, you can hide all this gobbledygook and make really clean code that generates arrays wherever you want them to live. And so Cocos manages the data layout for you all automatically. The most important thing about a GPU is it's basically a SIMD device. It's basically a shared memory parallel machine, which might have thousands of threads that are able to do things simultaneously does all the work simultaneously, basically shared memory parallelization. And the most common structure that uses shared memory parallelization is nested loops, nested for loops, or even just a single for loop. And so in C++, when you have a standard for loop, and you're using OpenMP to do shared memory, you'd maybe have a pragma OMP in front to tell the compiler to turn this into a shared memory. In Cocos, what you do is just use their construct, parallel for. You tell it a name for the loop. That's great for debugging. Don't have to give it a name, but you can. You tell it the range, and then you tell it what work to do through these lambda functions, which are part of C++. And basically, whatever is below this line gets inserted into this lambda, and that's the work this thing is going to do. And so this thing is exactly the same as the body of the loop, and that doesn't change. And so by having this abstraction, suddenly this can be turned into OpenMP if you want, and you're running it on a standard C++ compiler, or it'll be turned into CUDA, and this will be run in parallel on the GPU, or whatever other things. So you just have to replace all of your for loops with Cocos parallel fors. So you got to replace your data structures with Cocos views and your for loops with parallel fors. That's the most important things to know about your GPUs. And you can locate the data wherever you like. I'll just, in the interest of time, tell you, always put the data on the GPU if you can, because moving data back and forth is slow. So you want to make sure you stick the data where it's needed, namely in the GPU. And there's ways to do that using deep copies and dual views. The only skeleton in the closet about GPUs is their memory is incredibly limited. Only 80 gigabytes on the current generation of GPUs, which given their performance, 10 teraflops, is a very bad ratio of memory to flops. A normal node on a CPU cluster might have, nowadays, it might have a terabyte of memory on the node. And this GPU is as fast as the entire node and has 80 gigabytes, 12 times less memory. So you run out of memory on the GPU very, very quickly. And so you sometimes have to worry about this a lot. But if you can, make sure you stick everything on the GPU. Let me skip that. One other extra question.
No, I was just curious, is there just some hidden trade-off? Like why are the GPUs in such limited memory?
It's a trade-off. I mean, there's so much area on a silicon wafer, and the GPUs have chosen to use almost all that area for processing units and a very small amount for memory. And that's why they only have 80 gigabytes. And for most applications like mining Bitcoin, that's fine. However, for high performance computing, not so good. And so, until the vendors feel like the market really needs large memory GPUs, they're probably not going to build them very much. And, again, machine learning and so on probably doesn't use that much memory. So we're kind of stuck with what the vendors give us, and we have to just work with that. Reduction loops are one more concept you need to know about. And that's because when you're doing something in parallel and you're trying to come up with a single scalar number as a result of some parallel work, you have to do something special. If you've done any OpenMP programming, you know this already. So for example, if you want to take the maximum of an array and you do this in parallel, you can't just insert a max AKJ statement inside the loop, because that's a race condition. All you'll get out of that is whichever thread finished last, that's the value that will be stored in the max. And similarly in Cocos, that's the same thing's going to happen. On GPU, the same thing's going to happen. And so you have to make a special parallel reduce loop, which will do this in parallel, but it knows that it wants to return a minimum value. You can return min, max, sum, whatever you like. There's different forms of this parallel reduce. So you have to do something special inside the loop, and you have to use a special form of a parallel loop in Cocos to do reductions whenever you're taking min and max or whatever. And another little gotcha here is if you're looking really closely, you'll notice that this is the C, min function. What are you using? This is ancient, dinosaur, right? Well, that's because GPUs don't allow you to use the standard template library on the GPU. You can't use Amax or you can't use standard max, standard min because the GPU compilers don't know anything about STL. You have to use the C. Maybe that's changing as they change their compilers, but at the moment, that's true. It's even worse because there's probably other things in the STL you're using, like vectors or linked lists. Can't use them on GPUs because you can't use a standard template library. So you're gonna have to get rid of those structures and go back to simple C structures, or Cocos provides its own vector structure, which will work on GPUs. So this is parallelization. So let me finish by saying a little bit more about AthenaK. It's basically rewrite of Athena++ into Cocos. Again, the main reason for rewriting it is because Athena++ didn't have built into it this concept of multiple memory spaces and execution spaces. And so it really had a lot of changes required to do it. The goal was not to re-implement all the features of Athena++, which by now is a very mature and comprehensive code and a lot of person effort in it. It's really just to aim at exascale. It's to say, what problems would I want to run on Aurora or Frontier? And what do I need to do those problems? And just implement the things I need to do that. And so it's very simple code. Currently implements only Cartesian coordinates, no curvilinear coordinates, because all the problems I want to do are huge Cartesian problems, 10,000 cubed Cartesian boxes or something. It has the standard reconstruction and time integrators and Riemann solvers, full AMR framework, because that all ports to GPUs, no problem. Full AMR works great because the host manages all of that part. The GPU is just updating mesh blocks, and the host is busy doing all the mesh tree refinement and all the rest of that stuff. Task lists and so on are all there. It has both relativistic and non-relativistic hydro and MHD, both in GR and special relativity. Cooling. The big new things are radiation transport in full GR, thanks to Chris White's algorithm development. using a geodesic mesh, thanks to Patrick Mullen's algorithm development. So this is doing multi-angle radiation transport in full GR, typically 100 angles per grid cell, in order to look at radiation-dominated black hole accretion flows. And another new thing is we're venturing into numerical relativity. There's a full numerical relativity solver using the Z4C formalism implemented in AthenaK now. So we can do dynamical spacetimes as well as MHD and radiation transport in dynamical spacetimes to look at black hole merger problems with gas dynamics as well. And why? Because that's the kind of problem that exascale is going to be great for. You know, that's an expensive problem to do full numerical relativity, but you got an exascale machine, it can do it. It's no problem. You can run these huge problems. So that's an excellent target for this kind of application on those machines. And maybe I'll just finish up with this last slide here, because I have some examples of things I'm doing, but let me just show you the money plot, which is okay. Well, it's all well and good. How does it run? Here's the performance, hydro, MHD, special relativity, and general relativity for both AthenaK and Athena++. And AthenaK on a single core of a CPU versus the whole node, as well as an A100 GPU. And of course, on the Athena++, it only works on the CPU, so it's just a single core or the node. And so you can see that, first of all, the performance of AthenaK and Athena++ are very, very similar. Athena++ is a little bit faster for MHD, and that's because it's been vectorized so efficiently. And controlling vectorization in Athena and Cocos is a little more complicated, and we haven't quite got there yet, but we know what to do. We just need to vectorize AthenaK a little bit more. But it runs really beautifully on the GPUs. I mean, we're getting 250 million zone cycles per second and full 3D MHD, which is really enabling. And again, these ratios are about right. It's about 100 times faster. So we got 100 times more performance increase on a single GPU, and for 4 times faster than an entire node. Again, exactly where you should be in terms of ratios of peak performance. So it says that on a GPU, we're getting roughly the same ratio of peak performance as we would have gotten on a CPU. And this is where the performance portability comes into play. And I didn't do anything to the code except build it for the architecture. I didn't change any lines. I didn't make any changes anywhere except build it for NVIDIA A100 versus build it for an Intel Skylake processor. And so, and again, we've tried it on AMD and other machines. So for example, we have AMD processed in GPUs and NVIDIA GPUs. You can do this, again, distributed memory parallelization, excellent weak scaling in the sense that the performance is absolutely flat. Efficiency is above 95% across 4,000 GPUs. And so that's what makes it enabling. Okay, and I'll skip all the way to the end. I will skip almost to the end and show you the movie of merging black holes. This is it's pure gravity, full numerical relativity in AthenaK, showing you, I don't show you any waveforms here, but you can see the metric wiggling in the background as they release gravitational waves from this merger. And summarize with basically the largest HPC systems. Here's my major takeaway points. The largest HPC systems are built on these power efficient GPUs. Maybe that will change in the future. There's a huge push to build power efficient CPUs because everybody wants them in their devices. So maybe 5 years from now, power efficient clusters will be built out of ARM processors. I don't know, but right now it's GPUs. Programming these things is a bit of a bugaboo because they're so heterogeneous, and you got to manage the complexity that underlies the architecture. And that's probably not going to go away, even if they switch to some other kind of processor. And so probably it's best to rewrite or start from scratch to write a code that's able to exploit that heterogeneous architecture. And one way that I like, and there's other ways to do this, but the way I like is using Cocos. It's a very attractive way to enable performance portability. And right now it's production ready. We're doing some applications with it. And sorry for not having enough time to show it all. But anyways, I'm done. Thank you.